Hi, my name is Stephen Ying. In this brief presentation, I'll highlight how I optimized a cosine vector, a kernel used in QR code decoding by OpenCV. I'll show you how I improved performance by restructuring memory layouts using SIMD instructions and adding MPI-based parallelizations. Originally, the cosine vector kernel computed the cosine of an angle performed by 3 points A, B, and C in a straightforward scalar manner, shown on the slides above. For each triplet, it performed a series of subtraction, multiplication, and final division, 1 point at a time using vector point2f structure. As we can tell from the function here on the slides, this is a function used by QR code decode, get points near unstable points. It is selecting points from vector point and then performing the cosine vector in a scalar manner. While simple, this approach processes each element sequentially, underutilizing the CPU's capabilities. As a result, when the input size grew larger, the runtime increased significantly due to a lack of parallelization and cache-friendly data access pattern. So our solution to this is transforming from array of structures to structure of arrays, also used by Kenny in his kernel code. So I'll just briefly touch again here. Instead of vector of 2 points, we now store all x coordinates in one continuous array and y coordinates in another, like shown on the slides above. This change ensures that when we load data from SIMD operations, we get continuous blocks of floats. By aligning the data this way, SIMD instruction can efficiently access multiple points at once, improving cache locality and setting the stage for effective vectorization. So the next slides talk about SIMD vectorization that I do specifically for my kernel. So with structure of arrays layout in place, I apply SIMD vectorization using AVX intrinsics. Instead of handling a single point per iteration, we load A points, so A selected points in the specific functions, into 256-bit register and perform operations like subtraction, multiplication, fuse, multiply, add using MM256 instructions. We also unroll loops and interleaved computations, allowing the CPU to work on multiple batches concurrently. This strategy keeps the pipeline busy, minimize the idle cycles, and drastically reduce the number of cycles needed per operation. So to scale further, we introduced MPI parallelization learned from lecture. So the diagram illustrated here is how I manage the processes. So we have the root process, root 0 with rank 0, partitions the dataset into chunks and distributes them via MPI scatter V to multiple MPI processes. Each process then runs the SIMD optimized kernel locally on its assigned subset of data. After computation, we use MPI gather V to reassemble the partial results at the root. While MPI adds some startup overhead, once we have multiple processes running SIMD accelerated code in parallel, the improvements for large dataset is substantial. By combining data level parallelization, aka SIMD, with process level parallelization MPI, we achieve scalability and handle significantly larger workloads efficiently. And the performance result from our code shows that how the MPI plus SIMD outperformed the original code on the plot. And that's everything. Thank you for your time.